Hello guys, this is Subhash Gupta. Welcome to my channel. In the subject of data structures and algorithms, we are going to discuss key value representation of sparse matrices.
So let's see what contents are to be covered in this session.
We will be looking into what are sparse matrices, various representations of sparse matrices, what is key value representation, Python programming for key value representation of sparse matrices, operations on sparse matrices and their Python codes, advantages and disadvantages of key value representation of sparse matrices. In final, we will conclude the session with a recap of the topics. First of all, let us see what a matrix is. Matrix. A matrix is a rectangular array of numbers, symbols, or expressions arranged in rows and columns. Typically, a matrix is denoted by a capital letter A, B, C, and so on. Elements of a matrix are usually denoted by the corresponding lowercase letter with two subscripts. For example, Aij represents the element in the ith row and the jth column of matrix A.
Here, consider the matrix A with 9 elements represented in a rectangular array. If we have to locate 8 in the matrix, we will say it is located in second row, first position of the matrix. Thus, it will be represented as A21 as shown. Now, let's step into our main topic, sparse matrix. Here, typically we can say that there are two types of matrices, sparse and dense matrices. So what are sparse and dense matrices? Sparse matrix, a matrix in which most of the elements are zero. A sparse matrix is characterized by its high proportion of zero elements compared to non-zero elements. Dense matrix, a dense matrix where most of the elements are non-zero elements. Dense matrices are typically used in scenarios where the majority of data points are meaningful and non-zero. As shown in the below examples, we can differentiate a sparse matrix and a dense matrix. The most common operations on sparse matrices are addition, multiplication, transpose, storage and retrieval of values. Comparison between sparse and dense matrices. Memory usage. Dense matrices require more memory to store all elements, including many non-zero values. Sparse matrices, on the other hand, can be stored more efficiently by only keeping track of non-zero elements. Efficiency. Operations on sparse matrices can be optimized to skip over zero elements, leading to potential performance improvements in both time and space.
Then, where will we use sparse matrices? We have various applications of sparse matrices. In social networks, adjacency matrices representing connections between users. Most users are connected to a few others, resulting in a sparse matrix. In recommendation systems, user item interaction matrices in recommendation engines. Typically, users interact with a small subset of items, creating sparsity. In scientific computing, solving partial differential equations in engineering and physics, many elements are zero due to boundary conditions and discretization. In machine learning, feature matrices in machine learning where many features are zero for most instances, such as in text mining with word frequency vectors. Now, let us see what are the issues with storing sparse matrices in dense format. Memory usage, wasted space. Storing sparse matrices in a traditional dense format wastes memory by storing a large number of zero elements. For example, a 1000 by 1000 sparse matrix with only a few hundred non-zero elements would require storing 1 million elements if stored densely. Time complexity in operations. Inefficient operations. Performing operations on dense matrices involves processing every element, including the zeros. This can significantly increase the time complexity of matrix operations such as addition, multiplication, and inversion. For example, adding two sparse matrices stored in dense format would require summing each corresponding pair of elements, even if they are both zero.
Space complexity. Increased storage requirements. For large-scale problems, the storage requirements for dense matrices can be prohibitive. This is especially true for applications involving very large matrices, where the number of zero elements far exceeds the number of non-zero elements. For example, a 10,000 by 10,000 matrix stored densely requires storage for 100 million elements. If only 1% of these elements are non-zero, 99 million elements are unnecessarily occupying space. Data redundancy. Redundant data storage. Storing zero elements introduces redundancy, which not only consumes memory but can also slow down data retrieval and processing. For example, consider a large dataset where zero entries represent missing or irrelevant data points. Storing this zero unnecessarily increases the dataset size and can complicate data analysis tasks. Then, what is key value representation? Key value representation is a method of storing non-zero elements of a sparse matrix along with their positions. This approach saves memory by avoiding storage of zero elements. Now let us see what is a key and a value. Key. Key represents the position of the non-zero element in the matrix, typically as a tuple, row, column. Value. The non-zero element at that position. How key value representation works? Instead of storing the entire matrix, we store a list of key value pairs. Each key is a coordinate ij, and the value is the matrix element at that position. This method significantly reduces memory usage and can speed up matrix operations by focusing only on the relevant data, which are non-zero elements. Let us understand this with a real-life example. Think of a large city map where only a few locations are significant, which are having traffic lights, and some locations are not having any traffic lights. In the picture, you can see some red dots and some green dots. Let us consider the red dots indicate the traffic lights and the green dots indicate no traffic lights. If we represent this map with the traffic lights into a sparse matrix, you will get the given sparse matrix with ones represented as traffic lights are present and the zeros are representing as there are no traffic lights in that intersection. Instead of storing the entire matrix, we only store the positions and values of the traffic lights where they are present.
Implementation of key value representation using Python. Data structures used for key value representation. Dictionary, hash map. Commonly used data structure where keys are matrix coordinates and values are non-zero elements. Tuple or pair represents the key as a coordinate pair, row column. Steps to convert a sparse matrix to key value representation. Step 1. Initialize an empty dictionary. Create an empty dictionary to store the key value pairs. Step 2. Iterate through the matrix. Do through each element of the matrix. For each non-zero element, record its position, key, and value. Step 3. Store non-zero elements. Add an entry in the dictionary with the position as the key and the matrix element as the value. Here we have implemented a Python program using these steps. First, we have given the matrix and followed the steps, and we got the output for the non-zero elements positions. Operations on sparse matrices. As we have discussed before, the common operations on sparse matrices are addition, multiplication, transpose, storage, and retrieval. Sparse matrix addition. Adding two sparse matrices involves adding their corresponding non-zero elements. Only the non-zero elements need to be considered, reducing the number of operations. Procedure for this. Initialize an empty result dictionary. Iterate through the key value pairs of both matrices. Add corresponding values and store in the result dictionary. In the example, the matrix A has the non-zero values at positions first row, third column, and third row, first column. The values 3 and 1 respectively. In the matrix P, we have two non-zero values at positions first row, first column, and third row, third column. After addition of these sparse matrices, we will get the result matrix. On the right side of the screen, you can see the Python programming implementation of matrix addition of sparse matrices. First, we have defined a function for adding two sparse matrices. For the function, the inputs are matrix A and matrix B. First, we take a variable result and A matrix is copied into it. And then we start a for loop with values key and value from the B matrix. Then we take an if condition. If key is in result, we take result key is equals to the value in the result the position key plus the value, or else the result with the position key is equals to the value. After this loop is completed, we will return the result. Sparse matrix multiplication. Multiplying two sparse matrices involves only the non-zero elements, significantly reducing the number of multiplications. Procedure for this. Initialize an empty result dictionary. For each non-zero element in matrix A, multiply it with the corresponding row elements in the matrix B, and then sum the products and store in the result dictionary. In the example, we have matrix A and matrix B with non-zero elements at different positions. After the multiplication of these sparse matrices, we will get this resultant matrix. On the right side of the screen, you can see the Python program for multiplying two sparse matrices. For this function, the inputs are the matrix A, matrix B, and the number of rows and columns. For this, first we have initialized a result variable with an empty dictionary, and we have initiated for loop with the values I, K as the position values and V as the non-zero value in matrix A items. After that, another for loop is implemented with the value J in the range of total number of columns. Then we have started a if condition for the position values K and J in matrix B. And then a condition has been stated for the values I and J in the result matrix. If it is satisfied, the result matrix with the positions I and J will be equals to the addition of its previous value with the multiplication of B with the position non-zero value in the position of KG in the B matrix, or else the B matrix, the resultant value will be equals to the value with the B matrix K and J. Transpose of a sparse matrix. Transposing a sparse matrix involves swapping the rows and columns of the non-zero elements. Procedure for this. Initialize an empty result dictionary. For each non-zero element in the matrix, swap its row and column indices and store in the resultant dictionary. In the right side of the screen, you can see the Python program for transpose of a matrix. First, we have defined the transpose sparse matrix function with the input A, and we have initialized a resultant variable with an empty dictionary, and we started a for loop with values I, J as positions and value for the non-zero value in matrix from the A matrix items. The resultant matrix with positions Ji will be equals to the value. Then we will return the resultant matrix. This will print the transpose of the matrix A. Storage and retrieval. Storage. Using key value pairs for storing non-zero elements reduces memory usage. Retrieval. Accessing a non-zero element is efficient by directly looking up its position in the dictionary. In the right side of the screen, you can see the Python implementation of storage and retrieval of values. We have implemented a matrix of store with stored elements, and then we have defined a function to get the value with the inputs matrix and row and column. We will return the row column value of the matrix. Concluding the session, we have discussed about what is a matrix, what is a sparse matrix, and how it is different from dense matrix, how it is useful in real life applications, and what are the issues of storing sparse matrix in dense format. And then we have seen the Python implementation of sparse matrices, and we have continued with the operations on sparse matrices. Thank you for watching this video. Please like, share, subscribe.